All right, welcome to the Explainer. Today we're going to jump into a really cool puzzle at the heart of quantum mechanics. Imagine you've got a system with more than one particle. How do you figure out what their combined spin is, for the whole system? Well, it's not as simple as just adding 1 plus 1. It's way more interesting than that, and to guide us, we're going to be diving into chapter 15 of a real classic textbook.
And that book is none other than R. Shunker's Principles of Quantum Mechanics. I mean, this is the book for generations of physicists, so we are in very good hands as we start to unpack all this.
Okay, so here's our game plan. First up, we're going to ask, why even bother adding angular momenta? What's the point? Then we'll get our hands dirty with a simple example to really build up our intuition. After that, we'll lay out the general rule book, look at the actual mathematical recipe, the nitty-gritty. And finally, we'll get to the big payoff, this super powerful theorem that makes all this stuff so important.
All right, first things first. Why do we even need to do this? Before we get lost in the how, let's really nail down the why. What is the fundamental problem we're trying to solve? So this question here, it seems kind of basic, right? But the answer? It gets right to the core of this whole topic. You've got multiple parts, multiple particles. How on earth do you describe the properties of the entire system as one single thing? That's it, exactly. Think about something like a helium atom, right? It's got 2 electrons. If you want to predict how that atom is going to behave, like what it'll do in a magnetic field, you can't just think about the 2 electrons separately. It doesn't work that way. You need a new language really, to talk about their combined properties, their total angular momentum. That's the only way to understand the system as a single whole thing.
Okay, let's make this real. To really wrap our heads around this, we're going to look at the simplest case you could imagine. Just 2 spin 1/2 particles. Think of them as 2 electrons. We're going to forget about everything else. Just focus purely on their spin.
So this is super important. We basically have 2 different ways of looking at the exact same system. On the left, you've got the product basis. This is probably how you think about it first, right? Just describe particle 1 spin, then describe particle 2 spin. Done. And that's great if you want to know about the individual parts. But then on the right, you have the total S basis. This is a completely different perspective. It describes the system as a whole, focusing on the total spin of the pair. This is what you'd care about if you were measuring the entire thing at once. And here's the kicker. It's not that one is right and one is wrong. They're just 2 different languages describing the exact same physical thing. And this table here is like our Rosetta Stone. It's the translation guide between those 2 languages. See, on the left, we've got our 4 possible individual states, up, down, and so on. But look what happens when we switch to the total spin language on the right. They regroup. It's amazing. 3 of them clump together into what we call a triplet. They all act like a single object with a total spin of 1. And that last combination? It forms a singlet, a really special state that has a total spin of 0. So our 4 individual possibilities have basically reorganized themselves into a group of 3 and a group of 1.
And that right there is the entire game. The whole problem of adding angular momenta, it really just boils down to figuring out how to translate between these 2 descriptions. It's all about learning the rules to go from talking about the individual pieces to talking about the whole shebang. And once we crack that code, we can predict all sorts of cool collective behaviors.
Okay, so the 2 spin case was a great warm-up. But what about, everything else? What if we're adding different kinds of angular momenta? It's time to zoom out and find the general rules of the road for adding any 2, let's call them J1 and J2. Now, the first rule is a big one, and it's kind of surprising how much it limits our options. It's called the triangle inequality. And it basically says that when you combine J1 and J2, the total spin J can't just be whatever it wants. It's locked into a specific range, from their absolute difference all the way up to their sum. How cool is that? It gives us this really neat mental picture. The 3 angular momenta have to be able to physically form the sides of a triangle. So, okay, we know the rules, but how do we actually find these new combined states? Well, Shankar lays out this really elegant procedure. It's almost like an algorithm. Imagine you're exploring a mountain range. You start at the very highest peak you can find. That's our top state with the maximum possible spin. Then, you use this quantum tool called a lowering operator to take 1 step down at a time, mapping out every single state that belongs to that J family. Once you've mapped out that whole mountain, you look for the next highest peak that's totally separate from the first one. Mathematically, we say it's orthogonal. And then you just repeat. You keep doing this, finding the next highest peak and mapping its family until you've covered the entire landscape. Okay, we've got the big picture rules and we've got the procedure. Now it's time to get practical.
how do we calculate the exact numbers, the precise recipe for mixing the individual states to get the total state? For that, we need a special mathematical tool.
And that tool, that recipe, comes in the form of what are called Clebsch-Gordan coefficients. I know, it's a mouthful. But really, you can just think of them as the numbers in the recipe. They are the exact coefficients, the weights that tell you, okay, you need this much of state A and this much of state B to build the final state C. They're the absolute heart of the calculation.
So let's go back to our simple two-spin example for a sec. This table right here, this is the Clebsch-Gordan recipe for that system. And check it out, if we look at the column for the S equals 1, M equals 0 state, what do we see? We see coefficients of 1 over root 2 for the up-down state and 1 over root 2 for the down-up state. That's it. That's the exact recipe we saw before. This table just lays out all the precise numbers we need to switch between our two languages. Okay, last section. And you might be wondering, why? Why go through all this trouble? All this math, these coefficients? What's the point? Well, the point is that it leads us to something incredibly profound, a truly elegant and powerful result in physics called the Wigner-Eckart theorem. This, my friends, is the big payoff. I know. This equation looks like a beast, but don't worry about the symbols. The idea behind it is what's truly mind-blowing. What it says is that for pretty much any physical interaction you can think of, that's the T operator in the middle, you can actually split the calculation into two completely separate pieces. One piece has all the messy, complicated physics stuff, but the other piece, it depends only on the geometry of the situation. Just the shapes and orientations of the states. And guess what that purely geometric part is? Yep, it's just a Clebsch-Gordan coefficient.
And this is where the magic happens. Think about it. If that geometry part is just a CG coefficient, what happens if that coefficient is 0? The whole thing becomes 0. The entire physical process is completely forbidden. It just can't happen. End of story. This gives us these incredibly powerful things called selection rules. They're like cosmic cheat codes. They tell us, just by looking at the symmetry and geometry, which particle decays can happen and which ones are impossible, all without ever having to do the hard, messy calculation of the physics itself. So when you take a step back, what we've really learned here is that adding angular momentum isn't just some boring mathematical exercise. Not at all. These rules are woven into the very fabric of our universe. They dictate what's possible and what's forbidden. It's this beautiful, deep connection between abstract ideas like symmetry and the concrete reality we see around us. And it kind of makes you wonder, doesn't it? What other fundamental laws of nature are just sitting there, waiting to be discovered, hidden in the rules of symmetry and addition?